All right, hello everyone. Welcome to week 6 of ACM AI Reading Group. Today we have a special guest, Benson, who is the co-president for Cyber. We have kidnapped him. Oh my God, crazy. So yeah, we are keeping him hostage until he finishes reading group. So that's what he's going to do for today. He's going to talk about
federated learning attacks and defenses.
yes. Let's get started.
All right, so hello everyone. Oh my goodness, that was the Zoom thing. Where's my mouse? That's right. Oh, there we go. All right, so the title of today's talk is federated learning attacks and defenses. How secure is your privacy preserving machine learning? I guess if you want the membership code, it's Jordan Benson's romance. You know, I'll let everyone type that for a second. Yeah, quick show of hands. How many people are here from ACM Cyber? Any ACM Cyber? All right. Wow, the ACM Cyber officer in the back is not paying attention, unfortunately. But it's okay. Glad to see several folk here, and I guess everyone else is here from ACM AI, so glad to see y'all. Did everyone get the membership code? Okay, lovely. It's very memorable. I guess, sorry, a couple announcements for ACM Cyber. Quick plug. If you want to come to our workshop series, we have, a web hacking workshop on Monday, come to 4760. CS Town Hall, that's a thing that's happening next Tuesday. Come to that and tell the CS department your opinions on classes. You guys have great opinions. Cyber Lab is next Wednesday. We're going to be talking about infrastructure, CTF infrastructure. So if you want to learn about, cloud development, things like that, like Kubernetes, we're going to be talking about that. Pretty cool. PBR, if you want to come CTF with us, we're playing CTF exactly a week from now. And quick shout out to basically these are my boys. A small team of members of PBR literally flew out to New York like a couple of days ago to compete in CSOL finals, and I just found out today they got 16th overall in the entire world. So I think that's pretty good. So if you see any of these people, or maybe you're taking class with them, give them a quick thumbs up because I'm very proud of them. They did a really good job. So okay, Jordan roughly introduced me, so I'll just do a very short introduction of myself. My name is Benson. I'm a third-year computer science major. My pronouns are he, him. I'm one of the co-presidents for ACM Cyber at UCLA. So as you guys can tell, I'm not really an AI person, but I do like AI security and privacy. That's sort of where my background with this sort of stuff sort of comes from. So I'll be talking a little bit on that specific focus. I also do a little bit of hands-on hacking with our CTF team, Federated. I also do some research in security and privacy. I mostly do software security, but lately I've been starting to try and poke around with seeing maybe if AI security and privacy is pretty cool. But I'll be talking about some things I've been finding pretty cool lately. I will say one note. The way I like doing my talks is please feel free to interrupt me, raise your hand, ask questions. I have slides. I will be discussing the slides, but it'll be very lame if I'm just like reading off the slides the entire time. So feel free to just raise your hand. This is meant to be, a reading group, I guess. So feel free to interrupt, ask questions, be like, oh, that's dumb or something like that. And then, we can talk about it a bit. That's the best way to learn together. And I'm just here to present some really cool stuff I find. But yeah, feel free to do that. With that, let's start off with a little bit of background information. So, you guys are mostly, AI people. You maybe, started training your first machine learning models. I'm curious what you guys think is the most important thing to your model while you're training. Does anyone have any ideas or opinions or suggestions?
OpenAI says it's data.
Oh, okay, lovely. OpenAI's answer is pretty good. Anyone else want to throw something? Yes, in the back. High quality data you're building off of? Accuracy. Accuracy, okay, good performance. Yeah, that's a great benchmark of performance. All right, I great answer as well. Love the collaboration. So I'll throw up a few things that I was thinking about when I was sort of discussing this, I guess with myself. Model architecture, okay, always very important. Maybe the most important thing is instead, our hyperparameters. Those are really hard to find the best ones. So maybe those are the best one, most important things. Maybe, it's attention. Apparently they say that's all you need, apparently, maybe it's attention. Or
Come
maybe
to
it's,
ACM AI workshop next week to learn more about attention.
or maybe my favorite thing about AI, friendship, that's maybe that's the most important thing. You need good friends in order to train your model. But and I think Jordan stole from OpenAI from the beginning. Arguably, data is probably the most important part of training a model. As you can sort of see a bunch of silly photos I put up here. If you were ever part of like projects or something like that, you'll see, okay, I threw Cipher up there. I threw some word embeddings. I threw, does anyone know who this is? Yeah. This is the youngest billionaire ever. So I'll talk about that briefly. But as you sort of see, your data set sort of defines sort of what sort of tasks you're sort of tackling, of course, as you guys are very familiar with machine learning. But there's one particular type of data I sort of put over here. If you don't recognize it, this is like medical data. So they're testing whether or not a person based on, these parameters has diabetes or not. And this data is actually a little bit more critical than some of the other options we have over here, because it's a type of data known as personally identifiable information. To put it simply, that's simply data that helps identify or build up the identity of a person. And so, why is this sort of, more important than maybe, I don't know, like Cipher 10 or something like that? And the reason for this is because, it involves a person, right? And so as, ethical developers, as ethical AI engineers, you care about the models you develop, sort of sourcing proper data, but also sort of protecting the people who you got the data from as well. So obviously, this is a relatively benign data set, but if there was something more serious, like maybe the person, had cancer or not, that maybe this would reveal whether or not the person had cancer, then, you take sort of legal responsibility whether or not sort of what happens to that data. So maybe if that data leaks, then obviously that person's life would be, in a bit of an awkward situation that we would not want to put in. But yeah, the reason I put Scale AI over here and I put the youngest billionaire ever over here is something that I think, I forgot, I think you said that data needs to be high quality, and high quality data is a very incredibly hard task. That's why Scale AI, who specializes in making really high quality data sets, and this guy is very, very rich despite being very young, just because the task is very hard and the engineering sort of required to sort of construct these data sets is very important. So the sort of themes you'll sort of see in today's presentation is how can we balance sort of sort of our performance sort of considerations with quality of data with some of our privacy considerations here as well. But let's jump in from regular machine learning to my world, which is the world of trustworthy machine learning. What exactly is trustworthy machine learning? I'll sort of define it by sort of the subsets of trustworthy machine learning that I sort of have over here. But first of all, why should you care about this? As I was talking about before, you guys as machine learning developers, machine learning is a very powerful technology. So you want to make sure that you develop your technology ethically and you use the sourcing of data ethically. So what are some of the goals of trustworthy machine learning? You'll see this intersect with some other aspects of machine learning as well. You want your model to be generalizable. This is the same as performance, same as accuracy. If the model is, overfit on your training data, obviously that's not great. You want to sort of see that it's performant on unseen data as well. Robustness is, my favorite sort of topic. It involves AI security. So if you have been coming to our sort of ACM Cyber, ACM AI, maybe the workshop last year, or maybe the sort of project we have running this quarter, AI robustness is often dealing with things like adversarial examples, constructing what I would like to call optical illusions for AI and things like that. So making sure that your model not only is generalized to unseen data, but it's also robust against these sort of adversarial examples. Fairness is another popular one as well, where you sort of remove implicit biases. Obviously, a lot of data is sourced with implicit biases towards race, gender, things like that. I think ACM AI events often throw some events for that. And interpretability is a newer sort of topic that's getting a lot of traction, involving how we can explain the outputs of AI. AI is often a black box that obviously you don't always know what exactly is going on within, the hidden layers of the model. So using explainable AI to sort of as a new field where you can sort of understand the outputs of the model a little bit better to get a better sense of how the inner workings go. And privacy, this is the one we'll be working on. Privacy deals with a field known as privacy preserving machine learning. Is really interesting. So let's just jump right into it. So before I guess we talk about privacy preserving machine learning, what's the benefits of data? Obviously we care about the ethics side of things, but we also care about the money side of things as well. What's the fiscal reason that we sort of want to sort of care about this? As we sort of talked before, data is very valuable. Constructing high quality data is really hard. But the highest quality data that's often sort of derived is the data used in people's everyday lives. So one example is voice data. When you take, oh my gosh, I do not have my phone on you, but if you take your phone out, right, you have Siri on there, right? Siri is an example of an AI model that takes data from your everyday life. Every time you activate Siri, you sort of, query it to sort of, add more data specific to YouTube as sort of model. And then this sort of, tries to capture elements of your everyday life to sort of improve the robustness of the model, just because obviously your voice is quite different from everyone else's. Personally identifiable information, the big reason why it's a potential risk in privacy is because you may lose access or you might accidentally leak access to it. Like maybe you guys heard in the news about data breaches, things like that. Those correspond to the legal liability of the company sort of collecting the data. So obviously there are civil liabilities, which means that people can get sued. Companies can get sued for leaking this information. And these are very expensive. I have some statistics on some later slides, but these are sort of financial sort of costs that companies and I guess you as developers sort of want to sort of avoid when there's personally identifiable information. There's also something very recent in the past few years involving this idea called the right to be forgotten. In laws such as the European Union's GDPR, and California has something called CCPA. These involve collecting data through web cookies and things like that. So this law says that users have the right that if they request a company to remove their data, then it's sort of it's up to these companies to sort of comply with that. So sort of keeping sort of within sort of lines of this law, you'll see some of the cool tricks privacy preserving machine learning takes on to sort of make sure that the liability of the company is sort of moved away from sort of collecting the personally identifiable information. Okay, what is this privacy preserving machine learning? So to summarize, it's the set of algorithms, like 10 techniques, allowing us to perform machine learning on personally identifiable information without breaching the privacy of end users. That last part is very interesting because it sort of may be a bit paradoxical or confusing. To sort of simplify, the goal is how do we learn the features of a data set without actually having the data? Isn't that kind of weird, right? You don't need to see the data to understand how the data sort of contributes to your overall model. That's when I first heard about it, I thought that was very weird. But the high level idea behind why we're able to do this is because of statistics, right? So oftentimes when you're doing constructive machine learning models, you don't actually care about individual data points, you care about the overall statistical distribution. So if you only care about the statistical distribution and you don't care about the underlying data points, then let's remove the legal liability of having the underlying data points on you. Let's just get the thing that actually makes you money, which is the overall distribution. And then you can sort of save yourself from the legal burden of hiring expensive lawyers from our lovely law school and things like that. That's sort of a good strategy. So how do we sort of do this? Here's a classic example. So anyone here a lover of using emojis while they text? Anyone? Okay. Few emoji lovers. I'm a big emoji person myself, but when you open up your iPhone, you may have noticed that oftentimes when you start texting, the emojis you use are sometimes recommended to you if you open up the emoji console, things like that, or just the texts are sort of referenced to you. The way Apple sort of tackles it is a combination of techniques that we'll start talking about involving federated learning and differential privacy. But basically, to summarize, they sort of collect a statistical distribution on what the usage of your emojis and things like that to sort of figure out, okay, I have the distribution, but I don't have the underlying messages where I got this distribution from. And because I don't have the underlying messages, well, obviously I can't, see, Jordan, texting his sneaky, hookup link and things like that, later in the night. So Jordan's privacy is protected, but but I can provide Jordan a lovely AI model where I'd be like, hey, Jordan, you probably want to use, when you're texting Benson, you probably want to use a heart emoji, something like that. Yeah. All right. But it's a reading group, so I actually wanted to try and get us to do some reading. But before I get us to do this, does anyone have any questions on something I just said? Okay, great. Feel free to just interrupt if you have a question. Let's do some reading. Of course, let's warm up a little bit. I don't want us to, get overburdened. It's the weekend by, doing heavy paper reading. So let's start off by doing, some comic book reading. So if you want to follow along, there's this link here. It's federated with google.com. This is sort of a comic where, this is made by Google AI. So to explain federated learning, so I'll be sort of using this as a guide to sort of a presentation. Does anyone need a link or? I'll also have it pulled up on the slides if you want to just chill as well. All right. Just let me know if you need any help. All right. So federated learning, building better products with on-device data and privacy by default, an online comic from our favorite comic book artist, Google AI. So let's see what people Google are up to. Boss, I'm back from the conference and I know how we can win back our users. About time, our brand is in shambles. Don't worry. I learned all about a new approach that can handle our privacy concerns and improve functionality. It's called federated learning. Federated, what now? It lets us do machine learning while keeping data on device. It's resilient, low impact, secure, whatever, I'm sold. I'll give you a team of our very best interns, of course. And this person's not too pleased, but challenge accepted. Okay, everyone, we're gonna start with a hypothetical problem. Let's say we want to train a machine learning model on sensitive user data. And then we have the interns fooling around as always. You okay, buddy? You're a little damp. You're a little damp. Sorry, I would just get kind of worried about all this AI stuff. Understandable, very tricky. Where would you start? Oh, we have an eager beaver over here. It's easy. Get your app to upload the user's data to the server. Oh, okay. Maybe it's that easy. Hey, that's personal. Yikes. Can you say privacy nightmare? Okay, this guy is like dying. And then come on, I just want to make the app better. That's what we said before the incident. What happened? It seemed like a good idea at the time. You have this lovely app, Paul Pilots, until there was a bad data leak. Like I said, this was a privacy nightmare. But look, say you have an app, any app, just as long as it's not Paul Pilot, that relies on machine learning. The real world performance of your machine learning model depends on the relevance of the data to choose to train it. And the best data lives right here at the source of the devices we use every day. Oh, diagrams, deep lols. hang on. Isn't accessing that sensitive data the whole reason you're acting? But what if the data never left your device? Then I can't use it to train on Massey. Oh, like this guy named his AI model. Very funny. Welcome to the world of federated learning. We're about to train a centralized model on decentralized data. How exactly do we do that? On-device data can be used to train a smarter central model and improve our users' experience. But since there's no way we want to bring that data to the server, the training can be brought to the device. This better not drain my battery. Not to worry, devices are participable when they're eligible. Oh, we're not impacting users' funds at all then. Great. Let's say you 5 represent all of our users. Some of you probably have relevant data for the problem I'm trying to solve. And so, okay, we have someone picked. And so a subset of devices are selected to receive a training model. It's just a few megs, very small in memory size. It trains on your data for just a few minutes. And well, it sends your training results, not your data, to the server and disappears. And, very funny, these guys like, oh, I was starting to like this guy. Okay, so that's the first part of the comic. What exactly is federated learning? I'll try to put it more formally. Federated learning is this. Sorry. Let me first backtrack a little bit. So just a little bit of context. Since federated learning is quite complicated, and as I started digging into this sort of talk, I was like, oh wow, I will not have enough time to talk about all this. But I threw a bunch of things on here that we will not be covering that is related to federated learning that I do recommend checking out. So first thing is AI security. With trustworthy AI security is very fundamental. I am going to skip over the fundamentals just because adversarial examples in FGSM don't relate or are not unique to federated learning in this sort of context. So if you want to listen to a 2-hour workshop on it, me and Jordan put on one last winter, so this is pretty good. Hardware is actually very relevant, not just in the typical sense of using accelerated computing with the GPU, but particularly with privacy preserving hardware, and where your hardware is designed to prevent leakage of your personally identifiable information. What you actually learn is that there are hardware attacks where you actually, if someone throws out their very valuable GPU for some reason, you could chuck over and screwdriver, prop it open, see the bits on the hardware, and figure out and extract what the data used to train on it was. There is this paper by Professor Tian. She's the faculty advisor for ACM Cyber. So she worked on including cryptography to the GPU directly to allow for fast privacy preserving machine learning. Federated learning is a very difficult distributed computing and systems problem. It runs into quite literally all the same problems that distributed systems run into: fault tolerances, conditions, etc. If you want a quick crash course in distributed systems, I just threw this link up here. I think this is probably good enough. You don't need to go to anything else. Just read this, and then. But I'll be sort of skipping over that just because the complexity of the security vulnerabilities increases significantly once we're considering the distributed systems case. Policy and regulation, the law is very important when sort of designing how we can sort of build robust privacy preserving machine learning and federated learning. Particularly if you're interested in this sort of stuff, ask ACM AI events. I hear they sometimes do events with the ITLP, and Dr. Yan Tian, faculty advisor for cyber, is part of the Institute of Technology Law and Policy. So she works on improving data and privacy and security related policy to sort of tackle these sort of issues. But that bit aside, what exactly is federated learning? Well, federated learning was invented by Google back in 2016 in this pretty cool paper. As you sort of saw, it's decentralized training where user data is kept on the client device. So oftentimes it's used in IoT, embedded, and mobile system sort of cases. There are actually a couple ways you can sort of do it. I'll talk about in the next slide. But there's a few benefits to particularly doing this in sort of edge computing cases. If you are familiar, you guys have your phones, things like that. When you have your phones, your phones don't have the computational power that things like your laptop does and things like that. They don't have GPUs all the time. And so because of that, you're often limited by the amount of on-device machine learning you sort of can do. So federated learning is actually a really good cheat code because you can get really scalable equivalents of machine learning models. Like imagine you could train ChatGPT, but you don't actually have to buy all the NVIDIA GPUs and things like that. You could just use the CPU power of a distributed system of a bunch of different user devices, and collectively this would aggregate overall to the equivalent of the overall model. Each client runs a session where they train a copy of the model on their data and send the training results back to the server. So the weights are the only thing being transferred in between the server and the client. And these are aggregated together to build a large model. All right, a little bit of information dump after the common reading. Does anyone have any questions? Sure. Yes. Oh, interesting. So it's sort of like right to own your own compute, I guess, and things like that. I think it's like, so the question is should there be a law for this? I'm not a lawyer, so maybe go talk to a lawyer or a policymaker, things like that. But I think the general practice is that since you as the end user have control over your processing on your device, it seems like a user-related task at the moment, but maybe, it's obviously maybe a difficult for the current end user.
So do companies that typically do federated learning allow you to opt out? Is there a switch, or are you automatically off the bid, or what?
So we'll talk a little bit more on the next slide. I'll give a few examples of where federated learning is used. Currently, it seems like no, you are not opted out of federated learning. You will sort of see a few cases where you guys have actually used federated learning technology. Why is this not a concern about user safety and privacy? Well, because you can sort of think of this as the company running a different background process on your device's operating system. So it's already doing that for a million different other things on your operating system. So they say, why not just throw federated learning there as well? And obviously, there's no breach in data. The data is not leaving your device at all. Only the model weights are leaving your device. There's no breach of any current laws on data privacy.
Did mention the processing itself isn't really taxing to your hardware, or it kind of feels like mining Bitcoin from my device, so does that have any problems in terms of taxing the user's hardware unknowingly?
So I'll say my response to that question for the next slide, because I think the examples I was showing the next slides may surprise you, and I think you may deem them to be acceptable if you like the technologies that are on the next slide. Yeah.
I have two. First is it says it's only a couple megabytes.
Yeah.
So how would it work with a large model that's larger than megabytes?
Oh, so you're talking about, let's say if I wanted to train ChatGPT or something like that. So yeah, in this case, I think we'll talk a little bit more on the federated learning architecture, but essentially with the client server architecture, you could flip it around to treat the server, the aggregation server, as yet another client and pass it up to a yet another aggregation server. And this eventually scales back down to a node point 1, where you then have your overall large model there. But obviously you load balance a little bit, things like that. That's more of a systems problem, but it's the general idea is proof for it at scale.
And then the other part, or the other question I had is, this doesn't really help with if you're learning a strong relationship, say I'm Jordan, and every time I text my sneaky link, I type Jordan heart and then the name of the sneaky link. Even if that raw data isn't there, could that relationship not still be learned? And then when I'm on my phone and say I type Jordan, it'll suggest heart and then the name. Oh,
okay. So you're saying basically some data, right, to users is so unique that even if we apply some of these rules and things like that, couldn't we figure out who exactly that person is that data came from? Is that data still identifiable? That's something I'll actually talk about on a later slide. You're talking about something related to the nature of, I think traditionally in most machine learning data sets are usually something called IID. But with federated learning in case, you actually realize that a majority of your data is non-IID, which is that every data point is very unique. And because of that, it's sort of at base level, federated learning will not work without one simple trick. it's like machine learning engineers would hate this one simple trick. We'll talk about that in sort of the later slide. Yeah.
This is decentralization. The users like committing some crime, like the model picks up on it. You can't identify who it is.
So okay, so that's a very interesting, like over text message or something like that.
Yeah.
You're saying? Yeah. Hopefully, no. It's like the nature behind confidentiality and privacy is that no matter how much information you wanted to learn at different times, the standard is still the same. Your data is constantly confidential and constantly private, unless you're like the NSA and put in a backdoor. So
Can you just recover the data to know the weights?
can you recover the training data if you know the weight?
Model version.
Pratik is getting ahead to a later slide. Very good. Pratik is too good. He's thinking ahead to a later slide, actually.
Just a quick thing, but this is an IID. That stands for independently and identically distributed, or independent and identically distributed, which is basically the idea that the selection of data points, the order that you feed into the model, is not affected by anything. So if you think like in the case of just like training a classification model, we're just randomly selecting data points from the training data set. And you may imagine how like in the case of training AI models are supposed to generate all user behavior on just one user, that is not an assumption that you can make.
Thank you, Jordan. Any other questions? Great. Feel free to interrupt anytime. All right. So who uses federated learning? Actually, a lot of the companies you guys know. Google, Apple, Amazon are some of the biggest advocates for federated learning. And guess what? It's not a weird, obscure product that they trash like after 3 months. It's the products you guys use on your everyday phone. Siri, Google Assistant. If you guys have a Google Home at your house, if you guys have an Amazon Alexa, those all use federated learning. So this is not something that's stuck to an academic paper. It's something in production in the world today. There's a lot of different other interesting products. There's something called Gboard. Another thing that's pretty common as well, I used the texting example from before. That's used in production for message by Google, for particularly, I think Google has text selection as opposed to text prediction as well. Android devices all have this on there as well. The Apple keyboard for iMessage is the most classic example for a couple things. Apple is, if you don't know, the Apple keyboard is the reason why it's so good. You don't even realize that it's good, but the Apple keyboard, not the prediction, has spent like, ever since it first came out, has spent tons of engineering behind it. So you may notice that, or you probably should not be able to notice it, but this does happen, that when you start using your iPhone at first, your clicking will be slightly less accurate. And then as you use your iPhone more, it'll become more accurate. The reason for that is that Apple uses machine learning to increase the size of the key hitbox based on the previous characters that you type. So it does predictive for the size of the hitbox of the key. Just because when they first tried to just do uniform hitbox, this was like impossible. It was just like terrible. The touchscreen was never going to work. But once they added machine learning into the mix, then the experience was a lot better. Obviously, in order to do that, it's customized specifically for you. They need to learn your text and things like that. Obviously, privacy is a concern, so they decided to opt for federated learning. Yes, question back. Oh, probably just because obviously it's different learning context.
So how does this work? Like, do they have an individual model for each phone, or is it how do they customize it for each person?
Oh, so you're saying how is it customized for each person? Yeah, I assume it's just a model deployed specifically on the person's phone, fine-tuned on user data specific for that phone.
Sometimes I get this feeling that I'm talking to a friend, and then the next few hours, Instagram recommends me like a reel that's about that topic, even though I've not searched up on it. So is that like an instance of FL, and how do they integrate it like across from my phone to my Instagram account?
Okay, so you've actually talked about the enemy of FL. The enemy of FL. That's traditional machine learning where there is a breach in your data privacy. So, this is why if we go back to a previous slide, I talked a little bit about cookie laws and things like that. oftentimes when you go on websites, they have third-party cookies that track your advertising information, things like that. This is obviously a breach of your personal, data because it compromises your internet history and things like that. Obviously, Jordan doesn't want anyone looking at his internet history. And so, because of that, that's a breach of data privacy. That's something that Federated Learning tries to accomplish. Targeted ads, I think it's just very hard to sort of get into, or I don't know, I guess not sure if any company has looked into it, whether or not using privacy preserving ads is like something that's possible or something like that. But in the particular case of Federated Learning, no, it does not apply to Instagram ads. That's a different recommendation system.
Yeah. And also, some of you may have seen, like, especially with like iOS 15 or something, and onwards, it was sometimes App will pop up, and one of the bugs will be ask app not to track. That is basically iOS implementing this new thing where they stop apps being able to like basically exchange cookies with each other and exchanging the browser history and stuff like that. Always press ask app not to track. There's always never a benefit to letting these advertisers have your data. So just kind of putting that out there. And also the thing with like, I was texting my friends about this and I saw, like an ad about it. Part of it is also just kind of confirmation bias, because when you have talked about a thing with someone else, you subconsciously start to look for that thing when you're just like looking around. You're like, oh my god, that thing showed up, but image tab just showed up because that's just the algorithm doing its thing. Or maybe you're already generally interested in that thing with your browsing history, say in Instagram, and you are going to see that ad regardless. You have talked to your friend. So it's a very difficult thing to measure with these things.
All right, but does anyone have any other questions? Does anyone have a follow-up question for one of their? Yes.
For like the keyboard, is there like even any like major benefits of doing federated learning? Because I'm guessing like at this point they have a really good like base model, that just like needs to be tuned on an individual basis.
Right.
So like, I mean like I know that there's probably some like very like small marginal benefits, but are there ever like cases where it's like it's such a small benefit of like getting just a tiny bit more data on a really long-term model that you don't do it anymore?
Okay, so that's a really good question. So I'll sort of go for sort of discussing two sides of the point of this. I guess the relevancy of federated learning, some may argue, relates to the scale of your company and relates to how relevant it is. But scale is actually, you'll see federated learning actually has benefits that are sometimes scale agnostic. So particularly for the keyword case, the probably reason why most companies still have stuck with federated learning is probably limitations in hardware, simply because you can't fine tune well on your phone. I think there are actually some machine learning models or some machine learning libraries that are working on integrating, acceleration support for training on your phone. But at the end of the day, you're not going to beat, 4090 go burr or something like that, So you're obviously not going to beat the physical hardware that's on a server somewhere else in the world. And so, Apple, they're a big company. They want to optimize the user experience. They love, the customer experience, right? That's like their discussion. So I think because of that, they have the resources sort of put into this. But also there's, I forgot to link it on the slide, but there's a Harvard Business Review article that I read involving how small scale companies can actually benefit from federated learning as well. If you think about it, the biggest inequity in sort of tech, or I guess like with terms of your competition in the field, is your limitation by the amount of user data that you have. Federated learning gets rid of that advantage by saying you don't have any data. The benefit you provide is based on purely the services you provide, how good your architecture, your algorithm is, things like that. And so small scale companies don't have to spend tons of money on getting the hardware or maybe the cloud compute to sort of benefit from, to get up to scale with these sort of other companies. They can use the power of the distributed computing environment to sort of be like, okay, I have a really good app. I get like 2,000 users, and sort of build up my user base. I can sort of improve my overall product, my model, without reaching user data, and also without having to fight with the giant of getting the same scale of data that they do. Yeah.
So it seems that all the data is client side, and so there's going to be a smaller data set, and the data set is going to be skewed by the nature of the user. How do we counter like overfitting?
Oh, how do you counter overfitting? Okay, that's a good question. So, in some cases, like the keyboard example, it doesn't mind overfitting because those cases you are supposed to recommend specifically for the user, but you're talking about sort of like general cases. Like let's say just the general speech capability of Amazon or like Siri, where it's not like you're not worried about fine tuning. You just want to be like, I want to general, pick up on human voice overall. We'll talk a little bit more on the nuances of fine tuning in the federated learning world a little bit on one of the later slides, but the general idea is that because everyone is contributing a small, set of data. This is sort of like, you can sort of consider like a subset of the number of users your has as the equivalent to having a mini batch. And so because of that, you could do, there's some 50-50 research on batch normalization and federated learning. I'll talk about batch normalization, cryptographically secure batch normalization in a later slide, but a lot of these optimizations are, the benefit is just by having scale. Like the general idea is because you have scale, you're able to get a lot of the benefits of having a large starting data set or having a large, private user base that you would, have to fight for.
Considering that we aggregate the data that every user gives, does that mean that the recommendation actually becomes targeted? Like if I like to use the smaller multi a lot, but then overall the harder node is more popular, would I be recommended that the harder node would be more even though it's not?
All right, okay, so I see what you're saying. So the sort of the conflict we're sort of having here is if the benefit of federated learning is that I can aggregate more data, I lose the ability to fine tune the user. I think the end solution to this is just it depends on your ML ops, basically. It depends on where you're deploying your model for inferencing at the end of the day. If you're throwing the model on the server, then your task is to generalize, right? Obviously, if it's on the server, you're trying to generalize data as much as possible. But if you want to do it on, an end user device, maybe you're able to send a subset specifically to that user, but you don't breach their privacy. Maybe you can, deploy a smaller model, like in some edge computing devices, such as, or the example I know is like a very weird edge computing device I worked with a couple of years ago, but it's like their solution was that they just did all of inferencing on the CPU and their training was done on the GPU somewhere else in the world. Obviously, it's doable. There are like accelerated hardwares for inferencing specifically, so some people may opt for that. But I guess for the average case, they will just offer inferencing on the CPU. That seems reasonable enough. The compute seems.
Is it like, wait, so are we training like, is it just a small model that can fit on each of the devices, train there and also do inference there? But is it also like, are there larger models you're contributing towards that can't be run on specific devices? No.
Okay, so sorry, I think I confused everyone with the sort of distinction between personalized and the generalized model. So federated learning as a whole is, I guess, good GIF over here. You have, a copy of your initial model sent to a bunch of nodes. The nodes train to fine-tune the copies of the model on a subset of the data set. They have this updated set of weights. They send these updated sets of weights back to the server. They do a bunch of averaging. And when they do the averaging, this is when the larger models sort of built. If they want to fine-tune it and put it on a user device, that's actually an inferencing problem. So they would just shove it maybe on a small copy of the model on the phone or something like that. I think like there are papers on condensing weights or something like that. I've heard. I'm not too familiar with those, but you should ask these two nerds over here. Maybe they would probably have a better idea than me. But it's sort of so to summarize the question. The answer is sort of that it depends on where you deploy the model for whether or not it should be personalized or not.
Is like the node like an actual phone, or is it like a node that then like has a big model that split like the phone? Or does like every model you do with federated learning have to be within the training? Or
no, so oftentimes if you want to do like large models like GPT or something, you could obviously keep that model, copy the model on the server. But the small model you're producing is just the fine-tuned one on your subset of the data. Then you're sort of contributing to the overall larger sort of data. So it's like the copy you produce is small, but the larger model by the overall system is very large. So it can go up to the scales of billions of parameters.
so it's like you grab a bunch of little small fine-tuned super megabyte models and then like put them into like a massive bigger.
Yeah. I think the analogy is if you guys are familiar with ensembling, I think that's some of the math behind federated learning comes from ensemble. All right. Any other questions? Great questions. All right. So how does federated learning work? So there are actually two types of federated learning. I think I've been mostly referring to centralized federated learning. There's also decentralized federated learning. The way decentralized sort of works is that instead of having, a singular server, quote unquote, you treat every client as also a server, and you just sort of pass everything around. If you're familiar with Git, you can kind of think it like Git, but instead of repository, it's a machine learning model's weights, and the amount of data you're adding is your training data instead. That's the sort of abstract sort of thought process behind it. But yeah, the client's trained locally on device. Aggregation is done on the server. The loss function is sort of defined here in the federated learning context. It's actually quite simple. It's just simply weighted sum, or sorry, just a sum of all the, it's an average of all the the losses on the individual nodes, and then there's an additional condition where you need to achieve something called consensus. Consensus is a distributed computing term. Basically, all that means is that through a set of distributed algorithms, you need to figure out a way to make all of these x's agree on the same value. So eventually, they sort of converge to sort of some value. And sort of the example I'll show on the next slide, simple average is good. So any questions on that? I guess to sort of explain this visual here, this will sort of get explained a bit more on this next slide as well. But when you're sort of starting the process, the central server sort of chooses the architecture. It can be a very the great thing about federated learning is that you're essentially doing normal machine learning, just in an applied way, just very sort of spread out. And the central server transfers the initial model to the server. So this is like the initializations. I'll talk a little bit more about initializations on the next slide. Nodes, which are just the client devices. These ones could be iPhones, these could be edge computing devices, IoT devices, things like that. They train the model locally with their own data. Then, they send it back to the server pulls everything together, and then there's one giant model without accessing any of the user data. So, what are the phases of NFL? Well, you will kind of see that it's pretty similar to normal machine learning minus a couple of hiccups. Like normal, training, you need to do, initialization of your model's weights. So it just does an initialization same way as, the non-federated case. But the one catch is that you could actually initialize in two different possible ways. You could do random initializations on one place on the server and send that as the starting port, or you could do random initializations on each of the individual clients. Literature has shown that, the normal machine learning case with the initial, like a shared initialization starting on the server is better. But client's initialization is also possible. Maybe, and if you're for example, if you're in the distributed case, you don't have a centralized server, so you can't do a shared initialization. You have to do either cold start somewhere, or you have to just choose a distributed node as sort of the starting point. What you do then is something called client selection. The reason for this is that oftentimes with federated learning, you're dealing in the scales of minimum of millions, if not billions. The classic example is with Android. Android has 2 million phones. Each of those phones is a node in the federated learning network. And because there are 2 million phones, despite how much compute, Android may want to throw at it, that's a lot of data. They're not able to handle that much data at a given point in time. So they have to do the federated equivalent of batching. So the way they sort of do this is that instead of picking, a number, you just pick a fraction or percentage of the overall total nodes. And every iteration you go through the federated learning process, you just pick a random set of nodes based on the fraction of the overall data set. This is once you sort of pick this sort of random sort of set of nodes, then the central server keeps track of the random nodes and which nodes are assigned to do training. It sends the nodes, it tells them to sort of, start the training. It has like the copy of the network architecture and things like that. And so, it has pre-specified hyperparameters, and then, the models on the network does, the training. Once the weights are updated, it then reports back to the server by sending the copy of the updated weights back to the server. And then this stage of 2 to 4 sort of loops back a bunch of times through the set of iterations until you hit a hyperparameter for the number of iterations for termination. This is the same as, epochs, things like that, or, iterations within, I guess this is more analogous to iterations, depending on what the value of C is. But as you sort of see, you're iterating through the loop a bunch of times, similar to normal machine learning. It's just that you do this extra step of client selection. I forgot to click my little visual, but as you sort of see, first, the global model is sent from the central server. A bunch of copies are sent to each of the individual clients. Once the individual clients are sent, they do the training, they do gradient updates for the initial model, and then prepares for model aggregation for the next iteration. And then once all the model updates are sent back to the server, it does the aggregation properly. Any questions on this? Yes. Exactly. They repeat this process until the termination hyperparameter is reached.
Yeah, so every iteration, they send this model back and forth.
Yes, they do.
Woo. Brilliant.
So yeah, that's I'll talk about a little bit on the next slide, but yeah, network delay and network congestion is something to consider in the federated learning case that you don't have to worry about, running on a singular, distributed or a singular, CPU or GPU. So
can you basically do like a sort of a LoRa thing where it's like you let the local data points run a few iterations, so they come out, so they create this sort of like the model plus the sort of delta, like the amount of change they have made to the model. You take all those like changes and you put it into some global model and you try to do like an average or something to those changes.
oh, you're saying do basically like a weighted average.
Not necessarily weighted aggregation, but like instead of doing this every single iteration, let the local data do this training for a few iterations.
Right.
And then because they have done a few iterations, they send the model back, and using those like after a few iterations, you can do some like
would the weights be weighted? So at a certain point, you have to let everyone catch up to the same iteration, or you're trying to say you're trying to do
basically it's like how many iterations can we do locally before every single one of the models gets so out of sync that when we aggregate it together, it becomes not able to be like combined again.
Oh, I see. So
yeah, because currently we're doing this like every single iteration, right?
So I'm going to wave my hands and say that's the distributed computing problem. Just because yeah, you're running into fault tolerance and obviously the potential for different rate processing race conditions, things like that. I think that's resolved by some of the distributed computing parts of this. So I think there's like a fault tolerance. If you want to look that up on Wikipedia, I think that resolves a lot of the
like let's say you have you're training your models at 100 iteration, and then this one device is just really laggy. When we finish this first iteration, let's move back to start model. Do you know what's the typical approach for
Okay, so typically in this example as shown, each training cycle is done one iteration at a time. I forgot to mention in the reporting stage, if like a packet is dropped or something, if like the weights are gone, to the winds, then it does networking. It does CS118. If you got your SYN, your SYN-ACK, it doesn't got the if it doesn't get the SYN-ACK, then it probably has to do congestion control, things like that, and sort of try to resolve the data being lost. So that's a very classic networking problem. It sort of locks sort of at the reporting phase to be like, okay, this is where it tries to figure out what the heck happened, where are my weights, things like that. So any other questions? Cool. Oh yeah.
Wait, so why, we give all the phones a model, and we're train.
Yeah.
And then you said just do one iteration of
Yes.
like, and then what's the why not just do a bunch, or like what's the difference between doing more?
Do one iteration. I think to make it more like centralized learning. Because like, think about it this way. Would you try to do gradient descent more often on one arbitrarily chosen mini batch as opposed to like one mini batch, do you get several iterations of gradient descent above like a different? Like, do you see what I'm saying? Like,
Yeah, wait, so like, because if you did multiple iterations on all the phones, it'd be like stochastic, or just one example per update.
sorry, on all the phones you're saying?
Yeah, like, so you send it to the phone, right? Phone's there.
Yeah.
And then it's like, let it, one little train loop.
Yeah.
And then you instantly send it back.
Yeah.
It's like, that's a lot of, time. Why not let it, like, what's the problem with letting it just train like really well?
Oh, okay. So the problem is that you're not dealing with just one guy, you're dealing with n times c guys, which is like maybe in the thousands potentially. So essentially you're training it on thousands of sort of data points at a given time, and if you sort of, I guess, let that accumulate, then I guess you backlog your aggregation sort of part of the sort of. Does that sort of make sense? No?
No.
Okay, so your question was, why don't we just let like iterations run on a particular like mobile device and then let the other nodes just do whatever they want?
Like all of those, train them fully the best they can, and then just send them back to the main. Why do we do this thing of doing one iteration, send it back, and send?
Oh, so it's because you have an incomplete loss landscape. Just because your loss landscape is like, your loss function is defined just basically by one data point over here, which is obviously very complete, particularly because of a problem I'll mention on the next slide, because data points in federated learning, because they deal with people, are often non-IID. So because of that, the distributions are all very different. And if you don't check in more often, then it starts to get very hectic, basically. Does that sort of make sense?
Yeah, so it just works. It just doesn't form as well as
Yes.
fine tuning on each, sending, averaging, and sending that average and fine tuning.
Yeah, I think it's also I guess another sort of point is that the question is like, why do we just say, okay, for every one time for everyone, why don't we just like iterate instead of one time like 3 times or something like that as well?
It's like why do we have this back and forth? Like, I would think, oh, I want to train this federated model. I'll send it to the devices. They all fine tune as much as they can, send it back, and we're good. You just have it. Like, why is it this? Why do you need this constant back and forth of updating and changing?
I have a feeling it's probably just simply because you're dealing with non-I. Just because the data is just so different, and also you can't sample the entire data set. Basically, you have to sample a subset of the data set. So if you just keep working on here, you're gonna probably lose track of another, or you might lead to okay. So federated learning optimizers is a very cutting edge area of research, just because of another problem I sort of talk about. Basically, we can't take the square root, guys. It's kind of hard. So because of basically we don't really have optimizers here, this if you optimizer help us sort of make sure we don't do weird things like zigzagging across the loss landscape and things like that. So if basically we have an incomplete loss landscape, then we may have an incomplete understanding of where we're going when we're doing gradient descent. So
yeah, I think what you're saying is basically instead of training on the back, what if we just overfit the model of each individual data point and average them together? Yeah. Which in normal ML that would never really be an option because you couldn't parallelize them. You need to make a back to parallelize it, so I think something to be considered. But in this case, if each individual point is actually a different device, that we can be parallelized, but I don't know if it would be better. That.
Oh, okay. Maybe this is left up to empirical evidence. Maybe my logic thing is bad.
Do we even need a canonical solution from the server, or could we do a completely distributed approach where no one client has the canonical model weights, but they're all constantly updating off each other, so that it might not be the exact same, but it's close enough that you are in practical terms dealing with the same model?
Okay, so Jackson's basically saying I hate centralized companies.
Pretty much.
I think that makes sense. Like another option for federated learning is the distributed case where you don't have a centralized server and you basically can do a lot of similar stuff. It's just you treat a client as both a client and a server, but then obviously you then have lag when getting to like the leaf edges of your network because they don't have the most up-to-date version of your model. So distributed is possible, but that does run into the problem you mentioned in that there's a lack of consistency, which is it's another distributed systems problem. Yes.
So currently we're still doing the sort of like traditional gradient descent thing. Is it possible that we basically generalize this problem to basically treat instead the local clients as like basically reinforcement learning agents? Or no, because what you can do is you can treat them as black boxes, and instead of having to pass weights back and forth, you basically train a model that almost overfits in like their local behavior and basically tries to model the behavior of the current like current user. And that's not actual data, right? Because if you like regularize the model well enough, it won't actually contain information about the user. And thus, when you're training the like a centralized model, all you're doing is just saying, if I do this, what does this model think the user would do? And it passes that back. And basically now you have this like black box thing you can't gradient descent through because you're passing it through the internet. But you can use reinforcement learning methods to try to basically train on every single one of these separate devices.
Okay, so what I'll say is NERP's called, they want their paper back. So not sure how to answer that question. I don't know, I'll throw it out. Does anyone have any interesting comments on Jordan's thing?
So, John, I think with your idea, inserting reinforcement, you can insert the knowledge distillation with those modules, right? I think that would work even better because all anyone learns is speaking.
Yeah.
If you have like 1,000 feature models and one surprisingly larger student model, then you can't see.
Yeah. I guess the issue is the moment you start to pass these back and forth, at what point does it become a breach of privacy again? Like we're like if you keep sampling these models, then you should start being able to recover what the original distribution is, which is the problem itself.
The other thing I was thinking about is that if you fine tune it fully, then send it back, what you're pretty much sending is like a pretty well-defined definition of what the user data is. If you keep putting all together, send it back and fine tune it a little bit, it's like its user data is muddy with the original kind of. That's true.
So yeah, you guys are getting like very, very ahead of me. This is like a couple of the later slides, but great catch. We'll talk about that a bit more. Any other questions? Let's keep on rolling. All right, so federated optimization. We love optimization in the normal case. How do we do it in the federated case? So as I've been saying for like the past like 2 billion slides, most of the data in federated learning is non-IID just because people are actually very different. Because of that, it's very hard to use federated learning and pretend like we have IID data. So we have to sort of account for the data being very unique in sort of each sort of case. Also, there are class imbalances. We love class imbalances, right? Like basically federated learning creates the worst possible data set for us to use, non-IID, class imbalance as well. Because of that, this is just simply because obviously when you're running an app, some users scroll TikTok at 11 o'clock at night more than other users and things like that. So some users will provide more data than other users, and just simply because of that, those will lead to just class. Data is also very distributed. Why do I mention this? Is because the number of nodes, the number of devices will always be larger than the number of data points on each node. And if you're trying to go for performance with some of your, like learning, like normalization, like batch normalization is very difficult just because you have very small batch sizes and things like that per device, per data point. But that's if we're pretending we only are able to batch on individual devices. We'll talk about maybe how we can try to dodge around that on a later slide. Of course, everyone's been pointing out network issues. The packets can be dropped, the model weights can literally be gone to the wind. So due to Jordan pulling out my Ethernet or something like that. So network issues is something we also have to consider as well when we're trying to deal with federated optimization. So let's go with one of the classic cases of algorithms and machine learning. Let's do stochastic gradient descent, but in the federated context. So just to give people a refresher, the difference between stochastic gradient descent and gradient descent is that stochastic gradient descent is done over a mini batch. And so the benefit of doing stochastic gradient descent is that even though you are doing more steps with stochastic gradient descent every time you sort of try to optimize, each step is faster, so this will help you converge sort of faster. So in a similar sense with federated stochastic gradient descent, as I mentioned before, your mini batch size is actually just a fraction of your nodes. So your batch is just the number of nodes in your overall network. I guess the reference I pointed out that if C equals 1, this is just the entire data set, so this is just the same as normal gradient descent. But if C is less than 1, this is stochastic gradient descent. And so the process sort of goes like this. So the server first broadcasts the initial weights to all of the clients. The clients on the local end perform gradient descent locally. And once they sort of get the updates there, then they send it back to the server. Then the server can do the aggregation there. The one nuance to this is that there are actually 2 possible ways to do aggregation. You could either do it with the step being done at the client level. So here, at the client, the client level. So this is like this is the calculation being done on the centralized server. So because we already did gradient descent on the client, we don't have this learning rate times loss over here. And then basically simple average is sort of what our aggregation sort of technique is. One nuance as well is that learning rate can be localized. So you can have learning rate as an individual hyperparameter for each node, or you could also have it as a global hyperparameter at the aggregation server as well. So that's one possible nuance as well. Which is better is done and figured out empirically. So yeah.
For taking the average, is there any way of I guess sort of addressing the client imbalance issue where different clients are producing more or less data? Because if you're doing your optimization based off of one data point, I don't know, say not a lot of people text me, so get updates based off the text that my mom sent me in 1 day. That's it. Versus Jordan, he texts me all the time, and so exactly more robust data there. Are our weights going to be treated the exact same? Because my one text probably isn't as valuable as 1,000.
Okay, so I see what you mean. So if a particular user just simply contributes more, that's an optimization problem where you have to do similar to normal class imbalances, you have to do data augmentation on individual classes, things like that. So at the federated case, you still have to do data augmentation. Maybe you want to add an augmentation loop for whenever they contribute data at each of the individual client nodes. There's also the privacy related issue. You mentioned that if someone contributes more data, doesn't this make it more noticeable? This is solved by something called differential privacy, which we'll talk about in a later slide. But great questions. Any other questions? Cool. All right. Okay. So everyone always cares about code. So I thought I briefly mentioned code. Google, the TensorFlow loving people that they are since they invented it, has a library specifically for federated learning called TensorFlow Federated. I put a link here. We can go back to this slide if we have time to discuss some of the possible examples. Unfortunately, PyTorch, I love PyTorch, does not have a widely accepted library for federated learning at the moment. Maybe it's because it's a Facebook thing and Facebook data privacy. But one thing about TensorFlow is that it lacks something called secure aggregation, which we'll talk about in a bit. So if you are implementing an in production federated learning network with TensorFlow, you will need to account for secure aggregation. All right, so let's do a bad federated learning example. So, it's late at night, I go, Jordan, can you add your data to my model, please? Please? can you add your data to my model? So I do like a very bootleg federated learning network. I have like my training Python script on my computer. I ran it one time with my initialized sort of weights. I zipped this boy up. I sent it over to Jordan, and I was like, Jordan, hey, let's do it. What's wrong with this? Does anyone have any idea what may be wrong with this? Something mentioned actually earlier. Someone put this on. There's actually two things.
When you say add data to my model, do you mean like I use my own data and then train the model and then create a new PyTorch checkpoint?
Yeah, and then
Okay, so that. Okay.
this is a little tricky, but do you want to take a guess?
I guess it's like if it depends on how many iterations you want to run. If it's a very large number of iterations, then it's basically what happens is we keep almost like fine-tuning or continuously training a model on a completely different distribution, it will start fitting itself to that distribution. So because that model is now very, very much fitted to my own data, it may be easier to recover my browsing behavior and whatever behavior that you're trying to.
This is very true. You're actually getting one step ahead, and it's that, is it possible for us to recover, let's say I added some of my beautiful face to this sort of model. How is it possible to leak that, I'm part of the, I train model on my data? Does anyone, okay, who here, let's do a yes or no. This is like a yes or no question. Who thinks that, no, if I raw dog, my model, checkpoint and just send it over, I don't send any images over, Jordan could not possibly know that I added my beautiful face to this model. Who here says no? Oh, okay, interesting. Who here says yes, you can actually get the training data just from the weights alone, even without having any of the images? Okay, wow. You guys are either copying each other or you are looking ahead of my slides. But there's actually one more problem before I talk about the very heavily tipped upon sort of thing. So there's actually this problem involving federated inferencing. So let's think about this for a second. I am, let's say, I'm Google, I make billions upon billions of dollars. I spend millions training my model. I worked hard on this model. And then I was like, oh, I got to do this data privacy thing. So, okay, very casually, I'll just send my model to the client. I send my model to the client. I just lost my competitive advantage in the market. I lost my $10 million model, right? I just gave it away to, this loser Jordan who doesn't know anything about this, bro. I know my model. So model stealing is actually a big problem. Not even just in the training case, that's sort of a training case example, but in the inferencing case as well. Like if you're needing the model to be localized to the user, then you run into a problem where the user could basically just steal your model, right? They have access to your model directly. They could go sell it. They could start their own Google and things like that, even though they would get killed. But
That's more personal.
model stealing is a big problem in the federated learning case. So we need, the way you sort of fix this is you need a cryptographically secure way to inference. This is done by similar cryptographic protocols we'll talk about next few slides. But let's sort of go back to the example we were talking about before, but there's one additional step. Jordan has sent back the model trained on his data to me. What's wrong with this? Let's ignore we've already determined, let's pretend somehow magically that the security fairy, somehow sprinkled magical pixie dust and made this transaction secure. How do we possibly, jeopardize this part? Does anyone have any ideas? Yeah.
You like get the difference between the models and then figure out, oh, what got added or.
Okay, that's actually, you're getting even farther ahead of me. So that is a technique you can do. You will notice that, this lunatic over here knows both what was sent and what was received, even though objectively this is a black box. But there is like a difference. There's like a diff. I could figure out, maybe how to sort of extract that from the weights. But I'll sort of jump ahead since I think Pratik spoiled it all the way at the beginning. So you actually from the weights alone, you can get I will be able to extract just from receiving run 2 dot PTH. I'll be able to extract Jordan's beautiful face from this training data, or sorry, from the model weights alone. How do we do this? We're going back to my world with, instead of security related attacks, we're dealing with privacy related attacks. So what are privacy related attacks? These tackle sneaking confidential or personally identifiable information from something that they should not. Let's go back to our lovely comic. This person's very smart. Hold up. Can't you reconstruct the data from the results that are sent to the server? No way. It's got to be encrypted from the start, right? Okay, so that's sort of the answer. But basically, why can we reconstruct it? Because of something called model inversion. So model inversion is a privacy-based white box attack. What that means is that it gets data that's person identifiable, and white box means that it requires some information about the model. In this case, it needs a copy of the model weights. And so if you came to the AI security workshop, you learned about different threat models and things like that. Oftentimes in cases, if you just, don't put your model on the internet, you will be able to reduce all threat models to black box cases, which makes it very hard for adversaries. But with federated learning, you don't have that. Everything is white box. You're literally sending them a copy of the weights. So because of that, you always have to deal with the white box threat model. So because of that, what they can do is that they essentially, a set of weights is a bunch of matrix operations, things like that. You can sort of take parts of that, and you have basically this sort of set of weights that acts as sort of a generative function or a generative model, where you could throw in random noise from one end, and what is outputted from the inverse is a set of data that looks very close to the training data. So there are ways. This sort of attack goes hand in hand. Like the effectiveness of the attack goes hand in hand with generative vision research. Basically, as generative vision gets better and better, if you're able to guide generative vision models like dense diffusion networks better, you're able to reconstruct the training data better. Given that you sort of do this similar inversion, just because you have a better technique of doing image generation at the end. But if you guys want to see it in action, I actually have a notebook that I made last year. I go back, or actually, how am I doing on time? Oh, I'm not doing great on time. I will leave this in here. All right. Well, I'll just I won't run it, but because I ran it before, but I'll just show the output because the output looks kind of cool. So basically, this is a MNIST dataset, very classic, trained on Keras. If we scroll all the way to the bottom, we have this. Oh shoot, I'm going over this very long output blob on notebook. So we have a. Where is it? There's like this library that has a model inversion face attack. The original paper did a facial classification model, so you could leave which faces were in the data set, but we're doing it on MNIST here. And so if we do it with the inversion with like sort of a unique initialization, the initializations here are kind of bad, so you can't really see. But if you look at this initialization, wait a minute. That's 0, that's 1, that's 2, that's 3, that's 4, that's 5, that's 6, that's 7, that's 8, 9. So we are able to extract the training data. Maybe we could, get like, some better generative network on this, but basically with this attack, we're able to reasonably reconstruct what the training data is, which is pretty spooky, if I do say so myself. I'll keep on rolling. But sorry, did anyone have any questions? Great. Quick aside as sort of the system security problem. So people may be asking, or sorry, if you're not in the security field, this may not make sense to you, but there's something called TLS. TLS is an internet asymmetric encryption protocol. Basically, it's a set of cryptography. It's used in HTTPS, every website you go to. It automatically does this encryption over there. Basically, why can't we just do this? Why doesn't, spoiler, the solution to defending against these sort of attacks is, why can't we just do normal encryption? This is just, we'll talk about a fancy encryption on the next slide, but Why can't we just do normal encryption that we use every day on the internet? The problem with this is because this solves defense against man-in-the-middle attacks. So basically, if I send my model weights from here to here, if someone tries to intercept it, they will not be able to intercept it in between. This does not solve privacy problem. The server has to do with this asymmetric encryption. It has to then be able to decode the model weights. It could then still see what the model weights are. It can then do model inversion and then chain the the normal set of decryption back to this model inversion attack we sort of discussed, and then it could get the training data this way. This Google lady is saying exactly. It's not just encrypted. It can be encrypted with a key that the server doesn't have. That's the distinction. The server cannot have the cryptographic key that the model weights is sent on. But wait, you may say, if it's encrypted, how am I going to use it for training? Like the weights are then basically garbage, like binary data and things like that. How can we use it for training? That's where we get to this. Back to the comment. So secure aggregation enables the server to combine the encrypted results and only decrypt to the aggregates. On each device before anything is sent, the secure aggregation protocol adds zero-sum mask to scramble the training results. When you add all those training results, the mask exactly cancel out. Okay, let's take a look at this a bit. So what exactly is secure aggregation? Basically, secure aggregation relies on a few different cryptographic primitives. So we're going to the world of ACM Cyber now. Secret sharing is this idea that it's a cryptographic algorithm that relies on you need a certain number of people to have the information in order to recover the whole information. So let's say we have 3 people, it's like me, Pratik, and Jordan. Let's say each of us have a copy of the key, even though we have 3 different keys. And me and Jordan try to open the lock. We can't open the lock unless Pratik's there. So we all have to be there and sort of open it up. That's the idea behind secret sharing. There's this other idea known as oblivious transfer. Oblivious transfer is this really weird idea that someone can transfer information to this other person with this other person not knowing what the information is. Pretty useful for federated learning, right? We leverage oblivious transfer for secure multi-party computation. That's known as MPC. That's how we leverage oblivious transfer to something that we actually can run, doing things like ratings, rationalization, etc. The reason why this all works is because of zero knowledge proof. A zero knowledge proof basically is another hand-wavy cryptography thing that's pretty interesting. Basically, it's this idea that you could prove to someone else that you know something without telling them what it is. Very weird sounding. We'll take a look at maybe some examples on the later slide. And another set of encryption that might be useful is that oftentimes with federated learning, some people say you might be able to use something called homomorphic encryption. I'll briefly mention what that is on the next slide. But secret sharing is used more, even though homomorphic encryption is possible. We'll see a sort of example of why MPC sort of makes a bit more sense on the sort of next slide. Quick shout out, former cyber officers who I ripped the next few cryptography slides from. Yes.
Instead of using cryptography, can we just do something where so instead of training on just the user data itself, so let's say we're training on images sent by the user, we instead first train on just images in general, a bunch of images, and we train an autoencoder where we basically try to encode the image into some sort of latent vector that is then able to reconstruct the workable image. But all we do is the user gets basically when a user sends their data over, they send actually the autoencoder version of their data. So when we do eventually send the model back to the user, even if they do model inversion attacks, all they can see is the latent vector itself. So if they don't have access to the decoder, they can't reconstruct that vector.
So this sounds like you're trying to basically compress the data you're sending over.
Yes.
Right? And so can't you just do 2 steps where you first get, I guess the equivalent of auto inversion for decoders, basically, you create a decoder. You are able to create a decoder for this. Then once you get the latent vector, you just do model inversion on that. Isn't that possible?
But if our goal here is to say, I want to send you a model, and I want you to be able to use that model, but not be able to recover the data, if that's our entire objective, then I can be the only person who has both the encoder and decoder.
Oh, but is it then the problem that the data you send to the other person is useless, basically?
But they can still. Oh, I guess they have to use the model. Yeah. They could regardless. Yeah. I guess that makes sense. Yeah. Okay. Cool.
Just to clarify, so you're pretty much sending noise or masks to all the users, And that, like, when they then send it back, when you added all the noise, like it's all garbage, but then they add it all together, and that noise like cancels out the aggregation.
Yes.
Yeah. And then like, specifically though, it's important, you can't know who you're sending the noise to, or else you could just subtract that noise when they give it back, right?
So you do want to know who you sent it because you do want to subtract the noise. Because
I thought it was you just randomly, you have this like 5 components which all cancel out and you randomly send it to people, and then when you like only when you aggregate can you actually see the good data, because if you knew the noise you could just figure out the data.
so the trick here I'll show on a later slide is that not only you add noise, but the person sending the model back also adds noise as well. So because of that, even though you know your noise, you don't know their noise.
Okay. Would it also be safer though if you just didn't know the noise you gave to a person?
I mean, sure, you could just like press, random.random and look away. That also works as well.
Is there like a like cryptographic like way to like not know who got what component of the noise? Because I feel like that would be safer. But then you couldn't like, you know what I'm saying?
So I think maybe the cryptography slide in a bit might make sense. Yeah.
I think the only way cryptography is just like sample from any like symmetrical distribution with like a mean zero. The raw average distribution.
Oh, it doesn't matter. Okay, that makes sense. Yeah, you can do like 5 and okay.
Peek. Let's try to speed things along. So what is homomorphic encryption? For the math majors here, if you know what a homomorphism is, basically a homomorphism is basically when you apply a function and there's like some inner operation. Basically, it's this idea that if you apply the function after applying the sort of operation, and then you apply the function to each of the interval parts, then apply the operation, this is the same. I guess like an example is, like your functions, let's see, multiplication is the operation, and f of anything equals 1, I guess. Then yeah, f of bad example, but the trivial case, I guess, but it's like literally anything times, like n times k, f is 1, and apply to f is 1, and then you have 1 times 1, and then it's equal to 1, so blah blah blah. You have a homomorphism. That's a bad example, but there are more interesting cases we care about. Why do we care about homomorphism? We can apply it for something called oblivious transfer. What exactly is oblivious transfer? It's when you're trying to send data without it. So in this case, if we try to let Bob learn the complement of the output, or sorry, on the left side, Alice. So basically, they're trying to send this data to one another. Bob is trying to transfer B to Alice, but Alice should not be able to learn what B is. Very weird, but if we let Bob learn X of B, then Alice could just send both. But if we let Alice learn B, then Bob can send B and Alice can send X of B. So give me a second. Cryptography is not my strong suit, but I can hopefully catch up. So oh yeah, sorry. It's like, let's say if you like sum them together and things like that. Basically, this second line is saying, if Alice learns B, then Alice can, just like not reveal anything to Bob. And then if we let Bob learn X the complement of B, then oh god, my cryptography is very weak here. But basically, let's pretend oblivious transfer is literally black magic, because cryptography is literal black magic to me. Oblivious transfer is the fundamental underlying protocol. I ripped this from our cryptography slides. Basically, the main part we need to care about is, okay, so you can use homomorphic encryption with oblivious transfer as an extra effect. But the part we actually care about is why can't we leverage oblivious transfer? We can leverage oblivious transfer for multi-party computation. What exactly is multi-party computation? We have two people who have like values, and we want to compute like some function of those two values, but we don't want to let the other people know what that value is. You can do something called reconstructing a circuit. There are other things like garbled circuit, things like that. Bit out of the scope of this presentation, but basically abstractly, we have a cryptographic way to sort of do this. there's something called, we're going to do secret sharing, a particular type of secret sharing called additive secret sharing. So what is additive secret sharing? Basically, it's if we want to do addition, for example, what we could do is we could, take our value, we add some random noise. And so when this accumulates, player 2 holds back. Yeah, so when this accumulates, the information about the overall sum will get revealed. How do we sort of do this? Abstractly, if player 1, so x is equal to a plus c, y is equal to b plus d. When we sum together, addition commutative, it's just a plus b plus b, c plus d. And then we send this is publicly known information. Basically, we then can then subtract b, and then we can verify, okay, we have subtracted b, so then we know that the sum is a plus c plus some random number. This allows us to get, we don't know fundamentally what c is, but we're able to do the overall sum this way. Same thing applies for multiplication as well. We can do a similar sort of process as well. It's just that there's one extra step where you have to select some distribution, little PEMDAS. Then okay, start with the slide. So basically, by applying random noise to each of the parts, you can sort of leverage oblivious transfer to then have a few different fundamental functions that are cryptographically secure without letting either of the parties know what the other party has. This is really good because here's like the sort of algebra to sort of extract out that there is this works under multiplication, but let me go back. So basically, we then have addition. Addition then to sort of be extracted to multiplication. Then just throw out negative numbers, then you have subtraction, things like that. What in machine learning do we care about? Machine learning is just a lot of operations on matrices, right? Since it's just a lot of operations on matrices, what are when you do like any sort of general matrix operation and a subset, and at some point it just becomes addition multiplication, right? At the unit-based level, when you're going over, like if you do two matrix, like you do like a dot product or something, at some point it just becomes addition and multiplication. So addition multiplication is very powerful. There's some operations we need for some other machine learning functions, but with this MPC primitive, we're able to do basically a lot of machine learning functions with matrices that's cryptographically secure. So basically, if we have two nodes in federated learning, they could apply operations to one another without letting the other know what the underlying vector they had initially was. So sorry, let me pause for a second. I knew I just flew by basically an upper div course on cryptography, and I hand waved quite a bit. Does anyone have any questions on that? The fundamental idea to take away here is that we now have a cryptographic primitive where we're able to do multi-party computation without letting the other person know what exactly happened. That's good because then we could do the rest of federated learning. Any questions on this? Okay, I either lost everyone or everyone's having a good time. So, all right. People have been asking, Benson, what about those darn outliers? What if Jordan texts his sneaky link latent like so frequently that it becomes such a unique set of data? This is a problem known as model memorization, where the model particularly learns 8 data points. In a non-federated context, an example of this would be this paper involving how to extract training data from large language models. So in this case, basically, you should look up this person. His name is Nicholas Carlini. He is like a very senior AI researcher at Google Brain. Basically, every AI security paper is written by this guy in the history of the world. So this guy literally is the entire field of AI security and privacy. So go read his blog. He has a lot of very interesting stuff, and all of his papers are really good. But yet again, he strikes again with a very interesting paper where you can show that just in a traditional case from a large language model, you're able to figure out what exactly is the training data, similar to what normal modern version does, except this is in the case of a a generative model. Why is this important? Well, because in these sort of large language models, they're memorizing training data, because obviously a lot of training data, when you sort of shove it into a large language model, is very unique looking. And so because of that, then you apply a risk of running into techniques, even with generative models, and also you have the risk of running into model inversion again, where if you have outliers, then this is really bad, because then you are more prone to model inversion, as people are saying. How do we deal with this? Let's go to the comic. Okay, so the server can't see any single phone's results, but what if one phone has really unique data? Could that data be compromised by showing up inside the model? How do we solve this? Well, it's possible, but you don't want it to happen. For machine learning to work best, models need to capture the common patterns in the data, not memorize things that are specific to one phone. Wait a second, is that me? Looks like you're rare data, and we don't want the model memorizing that. This is why we have ways to measure and control how much a model might be memorizing. For example, watch happens if we limit how much any one phone can contribute and add noise to obscure rare data. The second part, adding noise, the first part is sort of an optimization, but the second part is something known as differential privacy. Differential privacy is more adding noise, is basically a well-established way to deal with the risk of model memorization, where shared models parameters might be too influenced by a single contributor. The way we get around this is for each data point, I'm also hand waving here because the math behind this is even weirder, because I went on the Wikipedia page and I was like, oh God, there's a lot of math, Winston, E-math that I do not remember. But basically, you can add a random noise to each data point such that the original data is obscured, but the distribution is the same. I think there's like a whole field of additive noise techniques. Like one of them is the Laplace transform, if you want to Google that as well. So if you apply these to your sort of data, you're then able to obscure your data but maintain the distribution, which is sort of core idea. This is very commonly used because, as we mentioned much before, there's a lot of non-I. Any questions? Okay, I'm running to the end because I have like 10 minutes before we're kicked out of the room. Oh yeah, now we can update our model and push out version 2, right? Not so fast. We've got more training rounds ahead of us, and then we want to test the model out before rolling out. But we don't have the data to test the improved model on because it's all on our user devices where it belongs. So that's where we'll test it. We'll test it on user devices. They safely train on device so that they can safely test the quality of the training where it matters most, on the users and in the hands of the users. This is great. We solve the privacy problem. While some phones are training our models, others are testing them. Training, testing, analytics, they're all tasks we can tackle privately and security with Federation. So obviously at scale, we can sort of get the benefits of doing this sort of large machine learning without running into sort of pipelining sort of issues. Okay, we get it. Can we update everyone's models already? But that was just a little improvement, but can we make it even better? Yes, we can. Training performance in federated learning. There are a couple relevant issues. One, client hardware is kind of jank. Most clients do not have a GPU, so even if they sort of have a small subset, they don't have the hardware acceleration performance. There are a couple different ways to get around this. One is obviously, well, it's okay, it's only like one data point, so it doesn't really matter. It's not going to take that long anyways. But another point is that there are improvements even at the base level. There is a library in TensorFlow called TensorFlow.js, where it could run machine learning just right in your browser. The way it does that is that it leverages a lot of Chrome's new browser APIs related to the GPU. It has something called the Web GPU API, so it's able to bypass a lot, or sort of improve upon a lot of the hardware sort of issues. Distributed computing is also something to sort of take into account as well, just because you're not limited to the single compute server. You're able to get basically a large set of compute by having sort of all these sort of data points. This is the next problem I'll sort of talk about. Our batch size is basically 1 every time we sort of like only consider normalization across like each individual thing. How do we get around this? Can we fix this? The way we sort of benchmark this is that we benchmark cryptographic performance in terms of 3 very common things. Computation, what's the big O, communication, what's our network sort of problems here, and round complexity, which is just the amount of messages for cryptographic data that we sent. Cool notes, linear and convolutional layers are actually the bottleneck for communication and computational complexity, but we just throw more computer in it to solve the problem. Privacy is very expensive, as you can sort of see. This is like training AlexNet on tiny ImageNet. Without taking account for privacy on just the CPU, this takes like 9 hours. And if we count for privacy, this like 960x the time. So obviously, privacy is very expensive. There are improvements, like the crypto GPU paper I linked before reduced this to 9 times, so a lot better. So so it's more reasonable to sort of account for sort of this. Batch normalization. This is like very critical when we try to do performant machine learning in the normal case with the non-federated case. How can we do it without with multi-party computation? Well, as we talk on a later slide, we have addition. What exactly is batch normalization? We have like our mean, our variance, things like that. What is it in the end? Well, this is really just a bunch of additions. It's really there's like a multiplication over here. So really, those parts of multi-party computation we're actually okay with doing. The bottleneck is this darn inverse square root, where we have the 1 over the square root here. This is actually the computational bottleneck with multi-party computation. There are ways to do it. It just takes a lot of rounds. And because of this, this is the thing slowing down federated learning using batch normalization in federated learning. There are some ways to speed up, like some papers. One of the papers I linked on the slides says they're able to get a performant version of 1 over the square root of x to try to get this performance, but a little sus. But the couple notes is if you know the fast inverse square root algorithm, like this Quake 3 algorithm thingy, this doesn't work in MPC because even though we are trying to calculate the values of floating points, we don't actually have floating points. What MPC does is that it does a weird conversion of floating points to integer values, then does multi-party computation on those. And floating point multi-party computation is a current area of research. So maybe if people can figure this part out, we can get to the rest of this other stuff a little bit better. This is just a sort of table showing what is the least, what is the computational complex, the round complexity of these cryptographic operations. Addition is obviously very cheap. When you get to like max, softmax, batch norm, those are very expensive operations. But what about security? Said no one but me. That's another consideration we have to throw in as well. How do we secure privacy preserving machine learning? Let's first get back to the AI, the normal non-privacy, the normal non-federated learning case. We have a lot of AI security threats going on in the original case. You have to deal with adversarial examples, you have to deal with model extraction, you have to deal with membership inference attacks, you have to deal with data poisoning, things like that. And this all just get a lot more complicated in the federated learning case. I don't have time to delve all into it. The concerns we have specifically with AI is that with confidentiality, don't leak your training data, don't leak your model. Obviously, in the federated learning case, that's really bad. Integrity, don't let people overwrite your model, don't let people overwrite your training data. Access, don't let people crash your model, don't let people destroy your accuracy of the model. Privacy, don't let people steal personally identifiable information. How do we sort of do confidentiality and privacy attacks? We talked about model inversion. There's also something called, we talked about model stealing as well, where you can literally just yoink the model and just use it. There's also something related with membership inference attacks. You could figure out whether or not a member belongs to the training data by sort of probing it in the middle of time, but that requires you be able to basically do 1 million inferences to the model. Normal system security actually is defenses against this. Data poisoning, also very tricky in federated learning. Basically, in normal data poisoning, what that is that you add adversarial examples to the training data, train the model on it, and this causes things to go wrong. In the federated learning case, you don't have this defense known as don't push your training data on the internet for people to write over. And so, because anyone can sort of by design contribute to the federated learning network, data poisoning is now very relevant. Here there are a few different types of data poisoning attacks. I don't have time to go over them, but feel free to stick around and ask it. But there are a couple of ways to sort of defend against this. One is very machine learning based, where you just do regularization. You do like defenses against this sort of thing to sort of defend against that. Also, you can do the systems security approach, which is my approach. There are like this. There's this paper by Microsoft research that goes around and uses a distributed ledger. Basically, they use blockchain to defend against data poisoning. Very cool. What is the impact of all of this? Why do we care? Well, 3 days later and several thousand iterations later, now can we update everyone's model? Oh, all right, I guess. This new model has learned directly from our users' data without centralizing any of it. Oh, such accuracy, and my data is still mine. Is this model going to keep learning as I use it? No, the new model is static. It's as smart as it's going to be until the next update, but it's really smart because it learned from thousands of users like you. So I was binge watching Star Trek for the first time. My keyboard out would already guess that Picard should follow Captain if it sees Riker follows Commander, right? Although I'm more of a Captain Ahab woman myself, so you guys talked a little bit about this concern. It's not so much personalized learning as it is collaborative learning. Sure, or if you just call it federated learning. There are a lot of places where utility and privacy schemes seem to be in conflict, but they don't have to be. Federated learning and analytics are new fields with established roots and tremendous rooms to grow, and they allow us to test and train on all kinds of devices, not just phones and tablets. Imagine training self-driving cars on aggregated real-world driver behavior, or how about helping hospitals improve diagnostics while maintaining patient privacy? And that's only the beginning. So what have we learned? That we can learn from everyone without learning about anyone. I so want to learn more. Quick comment from me. As AI interested people, you guys should, worry about development with respect to privacy and security. Data breaches cost a lot of money within the past few years, and it's increasing every year. There's also additional losses from falling reputation. Machine learning models are incredibly expensive to create. ChatGPT only takes $10 million just to retrain. You can save a lot of the engineering hours and money by paying for the sort of engineering thought process and sort of defense up front. Also, of course, you can practice good engineering ethics. You've all come so far. I think there's forever a home for all of you here at this company. Oh no, change of the plan, everyone. I've just learned that we are extremely bankrupt. Who wants to go start a new company? They could do that with federated learning. Everyone says yes. The end. Yep. That's the end of my talk. Oh, a quick set of acknowledgements. Thank you, Jordan, for finally letting me come nerd out here about federated learning. William Shan is an EC PhD here at UCLA. He specializes in this, specifically cryptography for machine learning in federated learning. Reach out to him if you want to learn more. I asked him quite a bit of questions. Thanks to the ACM Cyber offers for letting me blatantly steal their modern cryptography workshop slides from last year. Thank you to everyone here for coming to my talk. Thanks for coming. I hope you guys want your mind blown. I hope that was fun. I will be around to chat if you guys want, but hopefully that was at least somewhat interesting for you guys. There's a bunch of papers I linked. Don't worry about it. Oh, in the next 3 weeks, in week 9, you would want to come to Jordan's talk on generative Jordan models and unstable Jordans. Basically, CV's generative models, diffusion networks.
Diffusion models, we're going to talk all about diffusion models, how people are using them today, and how people are actually using diffusion models to not just generate images, but videos, 3D models, and everything else. And do controllable generation with or without training. It's everything that you want to learn about stable diffusion. And even if you have no idea how we're generating images, I will start from the very beginning and build it up. So definitely come. It's going to be the week 9 weekend because week 8 is Thanksgiving. So yeah, thanks for coming, everyone. Hope to see you in a few weeks.